is the same as the force between two current-carrying wires.
Okay, so here's a question for you. The wires are attracting each other, right? So the question is why?
Is the same as the force between two current-carrying wires.
Why would the wires be attracted to each other?
Because they're different charges.
Because there are different charges. All right, who said that?
Lucas.
Okay, look, I'm gonna give you 5 points for that.
Is the same.
All right, so tell me what you mean by there being different charges.
Well, one of them has a net negative charge, and the other one has a net positive charge. So they are going to ultimately attract each other as they're trying to get back to an equilibrium of electrons.
Okay, cool. So the opposites attract, right? That's what you're saying.
Yes.
All right, I'm gonna give you 5 points for that one. All right, guys. For whatever the reason, my dad, who happens to be a medical doctor, likes physics, and then he thinks he's good at it. And I don't know how they discovered this, but they rediscovering exactly the phenomenon that I'm showing here. Roughly about 20 years ago, when I was in graduate school, so my dad is pretty famous in Turkey, so he decided to have a press conference announcing that he finally discovered positive current. So he was pretty excited after the discovery got published. He said, "Ken, you're not going to believe this. I ended up discovering positive current." I said, "What are you talking about?" He said, they were doing this experiment, he and his buddy. By the way, his buddy has 5 different engineering degrees, including electrical engineering, and somehow they rediscovered this, something we discovered like 150 years ago. And then so he said, the opposites attract, right? I said, absolutely. He said, so if one current is positive, the other current is negative, right? I said, that absolutely not. Life doesn't work out that way. And I was really pissed that he actually had a press conference about it without even consulting me. I said, Dad, we both of us have the same last name, right? So you're destroying my future practically. I mean, if this is the direction you wanted to go, you could have used a condom, man. This is so stupid. So is there such a thing as a positive current and a negative current? We'll find out. All right, so what did Ørsted discover? He discovered that
Current causes magnetism.
Current causes magnetism, right? All right, so he discovered that the current caused magnetism. I wonder why this is not showing everything that it's supposed to. Okay, portion of the screen. Wow, this thing started to do some weird shit. All right, are you guys able to see this?
Yeah, we see lecture review material.
Okay, wow, so it's able to change places. This is weird. Okay, so let's go over the lecture review material. All right, so let's go over it real fast because we have to now pepper this with mathematics and then we need to build on it. So question number 1 is fairly straightforward. Guys, if you need extra credit, just jump in. All right, so we got the north and the south poles of a magnet. Where do we get the nomenclature from? We end up getting it because if you have a magnet and suspended through a string, it's always going to line itself up in the direction of the Earth's magnetic field. So the end pointing towards the north is going to be the north pole of a magnet. The end pointing towards the south is going to be the south pole of a magnet. That's it. All right. How do we know that the magnetic field lines start at the north pole of a magnet? We know that because you can trace the magnetic field lines, right, by using a compass. So you can map the magnetic field. Okay, so the effect of the magnetic field on the charges. If the charges are at rest, what happens to the charges? Nothing. Charges moving parallel to the magnetic field, what happens?
Nothing.
Once again, nothing. Charges moving across the magnetic field, what happens? If they're moving across the magnetic field, they will experience a force 90 degrees to their motion, deflecting their motion, right? So the right-hand rule is the rule that we end up using in order to figure out the direction of the magnetic force. So right-hand rule number 1, what purpose does it serve? It gives you the direction of the magnetic force, the force of deflection. All right. All right, so question number 8. We got a positive charge moving from the top of the paper to the bottom of the paper, so it's moving in this direction. Magnetic field is from left to right. All right, so using the right-hand rule, number 1, line up your thumb in the direction of the velocity vector. The fingers are lined up in the direction of the magnetic field, so the force is going to come out of your palm, so which means that the magnetic force is going to be pulling away from the page, coming out of the page. Question number 9 is displaced. It doesn't belong on this page, so we'll get back to it later. All right, so this is the stuff that you guys will be testing on Sunday. So your test is going to be on this as well as the stuff that we will cover this week. So the Earth's magnetic field protects us from charged particles. Only the charged particles come from space because the charged particles going across the magnetic field will become deflected by a force of 90 degrees to its motion. Any force of 90 degrees to motion is going to cause circular motion, so that becomes a centripetal force, so which means that the charged particles will wrap themselves around the magnetic field. And then they will be driven into the atmosphere at the north as well as the south poles, causing the northern and the southern lights. Magnetohydrodynamic propulsion system, here's the right-hand rule number 1. All right, I'm not going to get into the details, it's not that important. So what's the formula for the magnetic force acting on a particle? So the right-hand rule number 1 is going to be represented by this formula. All right, so V cross B, this is going to be a cross product, so force is going to be perpendicular to the plane of V cross B. That's what it means. All right, so here's the scalar form. Angle represents the angle between the velocity vector and the magnetic field. All right, so we answered these questions. Okay, what's the formula for the magnetic force acting on a current carrying wire? All right, it's going to be the same as this one. By the way, guys, the right-hand rule number 1 is used only for positive charges. Negative charges, use your left hand. All right, charge moving in this direction is going to cause a current along the length of the wire. Instead of current, it's just a scalar. Length of the wire is a scalar, except it's got a direction, so you can make this a vector. All right, so this cross this is going to give you the force that you're looking at. So once again, this is going to be ILB.
I'll get on my break.
All right, so that becomes a cross product. All right, I'm going to mute everyone. Just, if you need to say something, just unmute yourself. Okay, so the magnetic moment formula is going to be this. So the magnetic moment, well, I'm just going to call it the magnification factor. So I don't know what else to say. Or how much a circuit, the current loop is going to act like a magnet. All right, so bigger the current is, the more magnetized it's going to become. Larger the cross-sectional area of the loop is, the more magnetized it's going to become. The larger the number of turns is, the more magnetized it's going to become. So it's how much of a magnet it acts like is known as the magnetic moment. All right, so how much it gets magnetized is known as the magnetic moment. So that's the formula that we get to use. All right, the proper unit, obviously, current is going to be amps. Area is going to be square meters, and that's it. So the magnetic moment is going to be proportional to the current. Larger current, more magnetized it's going to become. It's going to be directly proportional to the cross-sectional area. Larger the radius is, larger the area is, more magnetized it's going to become. So, all right, so 19, 20, 21, kind of covered.
Professor, can I ask one quick question?
Yeah, go ahead, Lucas.
What is the quantity N represent? I think you're just about to explain it, but can you?
Cool. Yeah, very good. Give yourself 2 points for that one. N represents the number of turns that you have. Okay, so imagine this: if you have one single turn, it's gonna give you how much it acts like a magnet. I'm gonna call it the magnetization factor. And if you have 2 loops, obviously it's gonna act like the strength of it is gonna become twice as much. If you got 3 turns of a loop, then the magnetization shit, man, I'm turning into Trump. Magnetization factor becomes about 3 times larger. All right, so N represents the number of turns, number of loops that you have. That's what it is.
Thank you.
All right, no problem. All right, so how's the direction of the magnetic moment determined? Okay, so thumb, line up your thumb in the direction of the current. The fingers will curl in the direction of the magnetic field. All right, so this is the wire. Imagine that this is a loop. Just line up your thumb in this direction and then just grab the wire, and then notice that your fingers will curl in the direction of the magnetic moment. That's what it means. All right, so having said that, okay, this would be a good example. All right, so line up your thumb in this direction. Your fingers will curl in this direction. That's what it means. So your fingers will curl in that direction using your right hand, obviously. All right, so what's the formula for the magnetic torque acting on a current carrying wire loop? All right, so here's the formula. All right, so here's your magnetic moment in this direction. Magnetic moment is always going to be 90 degrees to the cross-sectional area. It's always going to be normal to the area, let's put it that way. And it's always going to, magnetic moment is going to try to line itself up in the direction of the external magnetic field. So if there's any sort of angle in between, like this angle, it's going to experience the torque in order to line itself up in the direction of the external magnetic field. All right, so what does the angle represent in this case? The angle is going to represent the angle between the external magnetic field and the magnetic dipole moment. Okay, in reality, let's put it this way. It's the angle between the magnetic dipole moment and the external magnetic field. All right, so this is in the opposite direction. All right, so let's change the direction of it. All right. All right, so what happens to the loop of wire if there's an angle between the magnetic moment and the external magnetic field? What's going to happen is it's going to experience a torque. So there's going to be a twisting force acting on it. All right, so okay, so question number 27. What's the formula for the magnetic energy stored in a current carrying wire loop? All right, so here's the potential energy of the loop. All right, so that's the amount of energy stored inside the loop. So what is the angle representing this formula? Once again, the angle is going to represent one. Why am I just drawing this in the opposite direction? So it represents the angle between the magnetic dipole moment and the external magnetic field. All right, so guys, this sort of stuff is, because you guys are engineering, this is the only engineering students, you kind of focus on that only. and your conceptual understanding is a little bit lacking. All right, guys, what is the potential energy represent? Potential energy represents the stored energy, right? So how do you store energy inside a loop of wire? If the current loop, how do you store energy inside a current loop, inside a magnetic field, placed inside a magnetic field? The only thing you have to do is just literally you have to grab this, and then you have to introduce this angle, right, between the loop, between the dipole moment as well as the external magnetic field. You have to kind of twist this. So you have to do work against the magnetic field. The amount of work that you do against the magnetic field is going to become stored in that loop as its potential energy. That's what it means. All right, so what that means is the magnetic field is also a conservative force field. That's the meaning of it. All right, question number 30. What did Ørsted discover? Ørsted discovered that the current caused magnetism. All right, so the Ørsted discovered that the current caused magnetism. What is the right-hand rule number 2? Right-hand rule number 2 is exactly that. Just line up your thumb in the direction of the current. Your fingers will curl in the direction of the magnetic field. All right, so 2 applications. If the current is coming out of the page, the magnetic field is going to be in the counterclockwise direction. If the current goes into the page, the magnetic field is going to be in the clockwise direction. All right. So what is the formula representing the relationship between the strength of the magnetic field and the current? So these are the ones we will get to shortly. So that's going to be this week's lecture. All right, so moving on to 42. Okay, so we will come up with mathematical expressions for these ones as well. All right, so the electromagnet, how does it work? If you have a current loop, it generates magnetism. So it just increases the number of turns on it. Now it acts like a magnet, and then you can increase the strength of the magnetic field by using iron. Iron is very easily magnetizable. So this becomes the North Pole, this becomes the South Pole. All right, so is it possible to wipe out credit cards using regular magnets? Absolutely not. Credit cards are fairly well made. By using extremely strong magnets, though, it's possible to wipe out credit cards. All right, so as magnetism generated by the atomic particles, according to classical theory, obviously you have a positive charge at the center. Moving about the positive charge, you got the negative charges. Motion of the negative charges, in this case the electrons, cause current. And according to Ørsted, current is what generates magnets. So which means that the atoms are microscopic magnets. So the orbital motion of the negative charges as well as the spin motion of the proton at the center, I don't want to say proton, the nucleus, let's say, is what generates magnetism on the atomic scale. So that's what it is. All right, so certain materials such as iron are easily magnetizable. The reason is they contain these small regions within which the atoms are already pointing in the same direction. Remember, guys, the magnetic fields are vector fields. Direction matters. If they're lined up in the same direction, the strength of the magnetic field is going to intensify. If they're pointing at random directions, the strength of the magnetic field is going to diminish. In opposite directions, they can cancel. All right, so how does heating destroy magnetism? Okay, so you have to focus on the meaning of heating in terms of physics. Heating is caused by the random vibrational and rotational motion of the atoms and molecules, which means that the randomized motion means that the magnetic fields of these atoms and molecules are going to be pointing at random directions. So that would diminish the intensity, overall intensity of the magnetic field within the region. All right, so the Earth's magnetic field, this is still a mystery. Surface currents are not responsible for it because surface currents would generate a magnetic field pointing in the opposite direction of the magnetic field of the Earth. Spin of the core can only spin in the direction of the spin of the Earth. It's got the same problem. Magnetic field would be pointing in the wrong direction. And the only way you can get the magnetic field to point in the same right direction, if the core is responsible for it, the core has to spin in the opposite direction of the spin of the Earth. This is not something that you can justify, given the fact that there's a tremendous amount of pressure on the core. And against the friction, it would not be able to spin against the spin direction of the Earth. All right, so we know that the electric currents are responsible for magnetism. How this happens is still under investigation, so we don't have a really good explanation for it.